Thank you and welcome everyone. This is ICTS tradition we have started before the pandemic, and I think we restarted it last year again. It's very good that many people take initiative every year to put everything together, and of course its success depends on the participation of the community of ICTS. So I'm glad this is happening. Since I haven't myself I have set a poor example. I think I've not participated in this myself, but then I saw in the schedule yesterday that they'd given me 15 minutes. So I thought I would take the opportunity to just give a little impromptu thing to sort of just to set the stage. So I'll say a few words about what I have been doing in this, but it's very sort of impromptu. So this is some work I have been doing recently, a lot of it with a postdoc called Edward Mazank, who's at Chicago. So this is something we call the simplest gauge string duality. Gauge string duality is a very fascinating subject of modern theoretical physics, especially in areas of quantum field theory, gravity. And it basically, in some ways, you can think of it as going back to Maxwell and Faraday about a kind of a duality between a field theory picture like Maxwell's and versus one of extended objects like flux tubes or string-like objects due to Faraday. So this idea has been there for a long time, but has been only gradually fleshed out. So it's still not something that is still well understood or in a very wide generality known as, for instance, in something like electromagnetism or even the strong interactions, what the corresponding dual string theory picture is to these gauge theories. I see this as a way in which strings are a very natural part of nature. I mean, that's sort of repeating it, but it's a very natural way in which strings emerge in natural phenomena, because you might otherwise think, oh, why strings? But to cut it short, let me just say that what we have been trying to look at is trying to simplify this to the simplest sort of setting. And we look at what might be called the simplest gauge theory. And the simplest gauge theory is something maybe many of you have actually seen in other contexts. So it's a zero-dimensional field theory, if you wish. I'll put it in quotes because it's just an integral. Basically, a zero-dimensional field theory is basically an integral, which I'll just write down. So a zero-dimensional field theory with, and we'll write it of a matrix field, like a gauge with what will be the analog of a matrix field. So of an n by n matrix, M, so Mij, which is, you want it to be sort of a gauge theory, so which is invariant. So by the way, this will be a Hermitian matrix. And invariant under M goes to U, M, U dagger, where U belongs to a unitary group of n by n matrices. So we'll look at a field theory which is in sort of gauge invariant in this sense, has this symmetry. In the simplest theory you can write is it's an integral, as I said, integral over these matrices, e to the minus trace m square, with some coefficients which you can put in if you want. But you see, this is because it's a trace over the n by n matrices. It's invariant under this unitary transformation. There's a very natural integration you can define here. So another way to think of this is to write this as these are complex, it's a Hermitian matrix, so it has complex entries, but which are related. So you can, so ij, so I less than j, you can write the measure in that form. And this exponent is just nothing but, so you see, this is just a Gaussian integral over just these matrix entries. And this is something actually many of you may have seen in other contexts. This is what is called the Wigner random matrix model. It appears in many contexts by now in various areas of mathematics, physics, engineering, and so on. It's a very powerful model, especially if you take people study it in the context of taking n very large, which is what we will do as well. I'll try not to set a bad example of going over time, but so this is the matrix integral, and you might compute what would be called gauge invariant observables. And the simplest gauge invariant observables you can compute are things involving traces. So a correlation function of traces of various powers of this matrix. You can compute these, and typically you take the connected piece, you can remove the disjoint piece. So these are a very natural set of, so average just means with respect to this integral, you just insert these and evaluate this and normalize it appropriately. So you can look at these. These are the sort of natural set of objects to consider in this theory. And it was realized long ago by 't Hooft that if I want to compute something like this, there's a very natural systematics to computing these. Physicists like to draw the contributions of a correlator like this as a sum of diagrams, Feynman diagrams. So what 't Hooft realized was supposing this is, I'm taking the case n is equal to 4. If I draw, I can draw Feynman diagrams, which correspond to, so this is a correlator, which is say trace m cubed power 4. So a 4-point function, as I said, with trace m cubed. That's because there are three of these lines coming out. I should have said something. You can see from the, so the basic thing that you use when you compute these correlators, if I have I1, J1, because it's Gaussian, this is up to some normalizations. This is the non-zero correlator, 2-point functions. So between 2 points, you have a non-zero correlator. And 't Hooft drew this in a very suggestive way. He drew these lines, I1, J1, I2, J2, and what sort of associated a so-called propagator to it. But this propagator now has 2 indices, so he associated a sort of a fat line with it. And these are these fat lines that are there over here. And so this is one contribution. There can be other contributions. You sum of all such diagrams. What 't Hooft realized So this is what leads to, I mean, you use this to compute these correlators. It's sum of diagrams like this. What Toft realized is that if you view these fat lines, they can be thought of as triangulating a surface, a two-dimensional surface. You can think of these as sort of the borders, so you can see triangles here, and this as covering a surface, and you associate each Feynman diagram is associated to a two-dimensional surface of so-called genus G. Two-dimensional surfaces are classified by the number of handles. So genus is the number of handles, G. And you can associate a two-dimensional surface to each of these Feynman diagrams. And moreover, you can, if I take n large,
Rajesh, you're at your 10 minutes.
Yes, I should stop. Thank you. Just a moment. So if I compute these correlators, they have an expansion in G, the genus G piece. And these are the same correlators that I was writing here. And there are these numbers you get here, K1 to Kn. For each genus, you get a set of numbers labeled by this. And these are very interesting numbers. And the question is there a string theory that reproduces them? And we've proposed a dual string theory, which involves so-called topological string theory, which reproduces these numbers, which is given in terms of a very simple set of quantities from a string theory point of view, how many ways you can map a surface like this into a sphere. So let me just write that and stop. To a sphere, or P1, in terms of what I call holomorphic maps. So those reproduce these NG. So this is a way in the simplest theory to sort of see how this gauge string duality can work, and it can, we are hoping to use it to understand more non-trivial gauge theories like those of Yang-Mills theories and higher dimensional theories. So this is a toy example, which we think has a lot of lessons. Okay, thank you.
Yes. So questions for Rajesh? Okay, then I thank Rajesh once again.